Hello everybody, it's Mrs. Lee. I wanted to go over the information in section 7.3. In section 7.3, we start to work with complex numbers. And what they want us to essentially be able to do in section 7.3 is operations with complex numbers. But before we can get to that, they need to explain what a complex number is. So up until now, when we took a square root, if we had something like the square root of 16, well, we were looking for what times itself will give me 16, and that would be my square root. So we know that the square root of 16 was either 4, or the square root of 16 could also be -4. And the reason that was because 4 times 4 equals 16, or because -4 times -4 also equals 16. And again, up until now, we said that when we took a square root, we had to be taking the square root of a positive quantity because there was no real number that when multiplied by itself would give me a negative value. And that's just because of the way our numbers interact with multiplication. Product of two positive numbers is always positive, and the product of two negative numbers is also always positive. So in order to expand what we could and couldn't do, we needed to create this imaginary quantity. So we have this value I, and it's always an I. And what I represents for us is the square root of -1. And if I is the square root of -1, what that must mean is that if I take I and I multiply it with another I, the result of that product must be -1. Because this is what all square roots tell us. If something is the square root of a value, then the product of that value and itself must be the number under the radical for my square root. So I is equal to the square root of -1, which is the same thing as me telling you that I times I will equal -1. And so for the first couple of problems that we work through in this section, we just want to practice using this concept of having I as a square root. So if we gave you the square root of -4, for example, well, this is the same thing as having the square root of -1 times 4, which is the same thing as having the square root of -1 times the square root of 4. And you don't have to rewrite it this way every time. I'm just going through a long explanation of what we get. Square root of 4 is going to be 2 because we generally find the primary root when we're evaluating these things. And the square root of -1, we just told you, every time we take the square root of -1, we get a value of I. So 2I would be the square root of -4. So what that means for us in shorthand is if I give you something like the square root of -100. Well, I know that the square root of 100 is 10 because 10 times 10 gives me 100. But because of that negative, not only will my root be 10, it will have to be 10I in order to accommodate that negative root. If I have something like negative square root of -49, for example, this negative does not transfer through the radical. It's not like a division symbol. This negative is just hanging out outside until after I take this radical. Well, the square root of -49 will be 7I. And because there was this negative hanging out over here, my answer is also going to be negative. And so I just want us to be able to evaluate these radicals. Sometimes for all of these, we're going to get an I in them because they're giving us these imaginary values. Sometimes the answer will come out to be negative because there's a negative hanging outside of the radical that's just waiting for us to take the root. So if I have a complex number, this I, it's an imaginary value. So we weren't lying to you before when we said that you can't take the square root of a negative value and get a real number. That's still not true. You still can't take the square root of a negative value and get a real number. I can take the square root of a negative value, and when I do, I'm going to have this I attached to it And this I is what we call an imaginary value. And imaginary values are not real. They're not real numbers. They're imaginary numbers, which means they don't live in the realm of reals for us. But all of these imaginary values can be written in a format a plus b times I. And if I have a number like this, we call this a complex number. And for this complex number, if I had both values, the a in that complex number is what we call the real portion, or the real value of this. So it's our real portion. And this bi, this is the imaginary portion of our value. So I can have a mixture of the two. So I could have a complex number like 2 plus 7i. This 2 is real and this 7i is not real. I can have a purely imaginary value, so I can have something that is like 5i. And 5i could also be written as 0 plus 5i, which means the real portion of my number is 0. The imaginary portion of my number is that 5i. And I could also have them both being negative. So negative 6 minus 12i. This is the real portion. This is the imaginary portion. And this I is not a variable. It's not like x was for us in our polynomials or our linear equations. That I is just indicating for us that we have an imaginary portion. But like the x, I'm not allowed to combine my real and my imaginary portion because they're not the same. And when we simplify expressions, we're only allowed to combine like quantities. And 2 is not like 7i because 2 is real and 7i is not real. So that's just the thing about what we can combine and what we can't combine. When we start to do our operations, we can only combine real portion with real portion and imaginary portion with imaginary portion. Which gets me to the next thing that we want to be able to do, which is operations with our complex numbers. So complex number operations. When we are doing our complex number operations, the first two that we run through are addition and subtraction. And when we are talking about addition and subtraction with these complex numbers, like I just stated, we can only combine real with real and imaginary with imaginary. So if I gave you something like 2 plus 4i plus 8 plus 13i. I know there are parentheses. Please don't get confused. Parentheses do not always mean multiplication. This group of values is being added, so there is an operation between them, to this other group of values. And when I do that, I'm looking for the real portion of my number. Well, I've got 2, that's real, and I have 8, that's also real. And I'm supposed to be adding those two together because that's what the operation tells me to do. 2 plus 8 will give me a real value of 10. And then I have two imaginary portions. I have 4i and 13i. And 4i plus 13i should give me a total of 17. And I will still just have a plain old I. Because again, even though they're not variables, in some way they kind of act like variables when we do operations. Because when we add and subtract them, only the coefficient in front of that I gets to change. The I itself does not get to change. Let's do another one. So if I gave you something like -9 plus 2i, and I wanted to add to that 6 minus 8i, for example. So then for my real portion, I have -9. I'm supposed to be adding to that +6. -9 plus +6 gives me an output of -3. And then I have this imaginary portion of 2i, and I'm adding to that the other imaginary portion, which is equal to negative 8i. Well, 2 plus negative 8 gives me negative 6 for the coefficient, and then I have my I attached to that. So when we are doing these, like I said, we're combining real with real and non-real with non-real. Let's do examples of other things we may see with this addition subtraction. So if I gave you something like 13 minus the square root of negative 9 minus, let's say, negative 8 plus the square root of negative 16, for example. If I have a radical, what the problem wants us to do is evaluate that radical before we go on with the rest of the problem. So we do a rewrite. 13 minus square root of negative 9 would give me 3i minus negative 8 plus square root of negative 16 would give me 4i. And now I can combine them the way we talked about. So I have 13 minus negative 8. Well, 13 minus negative 8 actually turns into addition. 13 plus 8 would give me 21. And then I have these imaginary values, negative 3i minus 4i. Negative 3i minus 4i should give me negative 7i. And so this would be my result from this operation we were given here. So far, so good, hopefully. Other things we're asked to do, we may be asked to multiply complex numbers. When we are multiplying our complex numbers, one thing I need us to remember, again, if we think about the definition, I is equal to the square root of negative 1, which means that I times I has to equal negative 1, which also means that I to the second power must equal negative 1. And so we'll be asked to do some evaluations where we're using I to the second power. For example, I might give you something like the square root of negative 16 times the square root of negative 81. I don't want us multiplying these two values together under the radical. I want us to evaluate each radical first. So the square root of negative 16 would be 4i. We are multiplying that with the square root of negative 81, which is 9i. When we multiply, again, if we think about what we did with our variable terms, even though I is not a variable, we multiplied the coefficients. 4 times 9 would give us 36. And then our variable, again, even though it's not a variable, in some ways it acts like one, I times I would have to give us I to the second power. So here I evaluated each radical. When I multiplied each coefficient, and then I said I times I gives me I to the second power. And I to the second power, remember we said anytime we see that, we're going to replace that I to the second power with its true value of negative 1. So we never want to leave a higher power of I in these expressions. Our job is to take it out and replace it with negative 1. So this is really 36 times negative 1, which really gives us negative 36. So this problem ends up equaling negative 36. Let's look at another one. So if I gave you something like 12i times, no, not 3, sorry, times 4i. When I multiply them together, I do the 12 times the 4, which gives me 48. I have I times I, which gives me I to the second power. And I to the second power, we're always going to take out and replace with its true value of negative 1. So 48 times negative 1, which is equal to negative 48. And then we can get more complicated from there. So if I gave you something like 6i, and then in parentheses, 2 minus 4i. Again, even though it's not a variable, in some ways we do our distribution just as if it were. So I would have 6i times 2. When I multiply those, again, it is only the coefficient that we're seeing change. 6 times 2 gives me 12i. And then I would have 6i times negative 4i. Well, 6 times negative 4 gives me negative 24. And I times I gives me I to the second power. So here I have this. But I want you to recognize that you have an I squared. And if we have an I squared, it's our job to replace it with its value of negative 1. So we have 12i minus 24. Instead of I squared, we'll write negative 1. Negative 24 times negative 1 gives me positive 24. So 12i plus 24 is what we end up with. And again, I just get more complicated from there. So for example, I may give you something that looks like 4 plus 3i times 5 minus 6i, for example. And if these were x's, hopefully we'd know, oh, if I see these two binomials multiplied by each other, it's my job to FOIL it out or to do a full distribution of these terms with these terms. We still have to treat it that way. So I have to do 4 times 5, which gives me 20. I also have to do 4 times negative 6i, which is going to give me negative 24i. I have to do 3i times 5, which should give me 15i. And I have to do 3i times negative 6i, which should give me negative 18i to the second power. So I did a full distribution there. And then just like before, if I can clean it up, I should clean it up. One thing to notice, we've got that I to the second power. We're never going to leave I to the second power. We're going to replace that with its value of negative 1. So I have 20 minus 24i plus 15i minus 18 times negative 1, which is going to give me 20 minus 24i plus 15i plus 18, because negative 18 times negative 1 gives me plus 18. I still have these 4 terms, but now I can see, hopefully, that some of them are alike. 20 plus 18, those are both real values. I can add them together. 20 and 18 give me 38. And I have negative 24i plus 15i. Again, I can combine those two values. They're just going to give me an I overall. So I would have to do negative 24 plus 15, which would give me negative 9. And I keep the I with it because it's a value that we had with those two things. So this is my real portion of my answer, and this is my imaginary portion of my answer. Let's do one more, and then we'll talk about the last operation I want you to do. So if I gave you something like 3 plus the square root of negative 16 times 7 minus the square root of negative 25. Here, again, before we do the operation, I want you to evaluate those radicals. Square root of negative 16 would be 4i, so this becomes 3 plus 4i. Square root of negative 25 will be 5i, so I'll replace that with 5i. And now here again, we'll treat this just like a standard binomial, and we will distribute. So 3 times 7 will give me 21. 3 times negative 5i will be negative 15i. 4i times 7 will give me 28i. And 4i times negative 5i will give me negative 20i to the second power. And then I have to clean this up. I squared, recall, is the same thing as negative 1, so it will be replaced with negative 1. Negative 20 times negative 1 should give me positive 20. So I have 21 minus 15i plus 28i plus 20. 21 plus 20 gives me 41. And then negative 15i plus 28i, I'd have to do negative 15 plus 28, which will give me 13 positive I. And so this is my result right here. So this is how we'll do our multiplication. We essentially sort of treat them like x's, but anytime we have I to the second power, we replace that with a negative 1. The last operation we have to complete in this section is division. When we are working on division, our goal here is to have no I in the denominator. And the way that we're going to get rid of I in the denominator is that our go-to move on these divisions is to multiply by what we call the complex conjugate. If we remember from previous sections, if we have A plus B, its conjugate has the same values except the operation changes to A minus B. And the reason we liked conjugates is because when we multiply conjugates together, A plus B times A minus B, those always gave us a difference of squares. And we're trying to force a difference of squares here, because if I square I to the second power, remember, always turns into -1, and that's not going to change here. So if I gave you something like 4 divided by 2 plus 3i, I don't want this I in the denominator. To get rid of it, I'm going to multiply by the conjugate. And because our conjugate is a complex number, that's why we call it a complex conjugate. And I'm going to put parentheses around this because I'm allowed to. And I'm going to multiply it by its complex conjugate, which is 2 minus 3i. Same exact values, just a different operation, no longer addition. Now it is subtraction. But again, because I'm simplifying here, I'm not allowed to just randomly multiply the denominator by something. If I do it to the denominator, I have to do it to the numerator as well. So then I'm going to do a distribution on the top and a distribution on the bottom. 4 times 2 is going to give me 8. 4 times -3 will give me -12i. I'm going to do the full distribution this time, and then from here on out, we'll just start skipping it. So 2 times 2 will give me 4. 2 times -3i will give me -6i. 3i times 2 is going to give me +6i. And 3i times -3i is going to give me -9i to the second power. This I to the second power, we are going to get rid of and rewrite as -1 because I to the second power is always -1. What you should notice also is that -6i and +6i, these are exact opposites of each other, so therefore these two terms cancel out. So on top, still left with 8 minus 12i. On the bottom, I have 4. It was originally -9, but -9 times -1 gives me +9. So I have this, and then I simplify. I still cannot combine the real and imaginary portions in the numerator, but I've got 2 real portions down here, and 4 plus 9 gives me 13. So even though they asked me to do a division originally, I know way back here, what did we say to do? We were asked to divide. When we divide, we still end up with a ratio. This ratio no longer has I in the denominator though, and that's our goal, is to get rid of I in the denominator. Let's do another one. So let's say I gave you something like I over 2 minus I. Here, again, my goal is to get rid of that 2 minus I. I don't want an I in the denominator. I'm going to get rid of it by multiplying by the complex conjugate, 2 plus I. And if I do it to the bottom, I must do it to the top as well. I times 2 will be 2I. I times I squared, I times I will be I squared. 2 times 2 will give me 4. 2 times 2i will give me 2i, negative 2i, and negative I times I will give me negative I squared. Again, these middle two terms are always going to cancel for us. 2i minus I squared, well, this I squared has to become negative 1, just like this I squared has to become negative 1. 2i plus negative 1, I would just write as 2i minus 1. On the bottom, I have 4 minus a negative 1. Minus a negative 1 becomes plus 1. Your book may rearrange these because we like to have our real portion in front and our imaginary portion behind. So it may write this as negative 1 plus 2i instead of 2i minus 1. They're technically the same, so don't worry about that. And it will be over a value of 5. Let's do one more, and then we'll close this up. So if I gave you something like, let's say 5 minus I over negative 7 plus 2i, and I'm going to put it in parentheses even though originally it was not. I don't want this I down here in the denominator, so I have to multiply by the complex conjugate, which means we keep the same values, we change the operation, so negative 7 minus 2i instead of plus. On the top, I would have to do a full distribution. 5 times negative 7 gives me negative 35. 5 times negative 2i gives me negative 10i. Negative I times negative 7 gives me positive 7i. And negative I times negative 2i gives me positive 2i squared. I could FOIL it out on the bottom, but I don't have to. What should happen is that I should get negative 7 times negative 7, which is 49. I should have minus, and then I should get 2i times 2i, which would be 4i to the second power. Those two middle terms are always going to cancel each other out, so I don't necessarily need to write them if I don't want to. And then we clean up. All of our I squareds will become negative 1s, which means I now have negative 35. I'm going to combine these two. Negative 10i plus 7i gives me negative 3i. And then 2 times negative 1 gives me negative 2. On the bottom, I have 49. Negative 4 times negative 1 gives me positive 4. So then negative 32 minus 2 gives me negative 37. Minus 3i all over 49 plus 4 gives me 55. So this is as far as I can go with that problem, and I'm done doing the division that we were asked to do. I hope that helps. Please let me know if you have any questions. I'm always happy to answer them. Thank you.